So today I want to talk about three measurement metrics that you often are going to see in any visualization papers or any computer vision or 3D reconstruction paper that you're going to read, and they going to appear again and again. So it's PSNR, SSIM, and LPIPS. So you're going to see these metrics kind of almost in every 3D reconstruction, in model measurement paper, or you're gonna see it in computer vision papers. So we're gonna talk about why we are using these three metrics, what each of them mean, and how each of these metrics kind of hide some of the facts about the image and the reconstruction result that the other ones are kind of catching. So we're going to start with the PSNR, which is the most, kind of can't call it the most literal one. So what PSNR does is peak signal to noise ratio. So what does that mean? It means that, let's say this is two corners of an image. So we've got 4 pixels here, 4 pixels here. This is the ground truth, and this is your reconstruction. So what PSNR does is that it compares pixel by pixel. It compares the ground truth 0 pixel to reconstruction 0 pixel. So the same pixel and the same index. So we're gonna compare this pixel with this pixel in this, and we're gonna subtract them. And then we square the error and then average them. PSNR is literally measuring at the pixel level what are the differences between these two pictures. The problem is that when you are computing the R2 error, what is going to happen is that a lot of times for human eyes, like pixel to pixel doesn't really matter. And if you have a model that like you train it in a way that only cares for PSNR value to be good, then the model learns that as long as it creates blurry images, it's gonna hit this metrics signal. So an image that is blurry and to human eye looks really awful loses compared to that an image that is blurry wins compared to an image that is really sharp but has like a minor error in his area. Also, imagine that I have 2 images and I have my ground truth, and then I'm gonna go shift all of the pixels 1 point. So if I shift all of the pixels, like these pixels are gonna be different, but then the rest of the image is gonna be the same. And if I do that, then your PSNR is gonna drop so much because all of these values are gonna be wrong. But to a human eye, this is gonna look really close. You wouldn't even notice it. So another thing that we need to talk about these metrics before we go further is PSNR higher is better, SSIM higher is better, LPIPS lower is better. And when we say that, what we mean is that this more similar two images are, their PSNR is going to be higher, SSIM, the more similar they are, is going to be higher, and LPIPS is going to be lower. The range for this is 0 to infinity, and we measure it by decibels. For SSIM, the measure is 0 to 1, and LPIPS is also 0 to 1. And with LPIPS, lower is better means that the more similar they are, closer you get to 0. So PSNR now, because it measures pixel by pixel, really favors blur. So this is where it falls short. So now let's go to SSIM. So with SSIM, it's a structural similarity metrics. So for structural similarity metrics, what we are gonna look in an image. So if I have this image, and then I'm gonna run a window on this, and I'm going to move this window like this, and I'm going to move it like this to find the edges. So SSIM really cares about like the structural similarities through contrast. So human eye is very good at detecting shades of gray. And when we have those light and dark, it helps us find the edges. So what SSIM does is that it works in the grayscale first. It's not RGB. So it's trying to find all these edges as it moves these moving window along the image and compares two images with each other based on this window. The problem with having a window that you have is that this window doesn't, like, it has width and height, right? And based on the width and height, it understands the image. So anything bigger than the window that is wrong in the image, it's not going to really figure it out. So you can have like two images that kind of look a lot alike, and one of them has, let's say, like, we used diffusion models on it and created some like awful looking objects, and half of that object is in one of the windows and the other half is in the other. SSIM wouldn't really detect it, even though a human eye would catch it in a second. I was like, that object looks wrong. So SSIM, because of the window it doesn't get bad objects as a whole. So that's where it falls short. So LPIPs. So we created LPIPs. It was in 2018, and the idea was like, what if we use machines? What if we use deep learning to allow AI decide how close two images are? So we use CNNs. They give two images to CNNs. So we give our ground truth and our reconstruction to a bunch of CNNs. And the CNN decides like how close these two are. So it gives us LPIPs. And the way that they trained this model is based on, they asked people to like score these and gave it to the model and trained it like that. So it is really close to human perception of the difference between images, but at the same time, it understands images and it describes similarity the way an AI would, not the way that a human would. It's just when it says that something visually looks close, it's understanding of what usually looks close look like. And because of that, in LPIPs, you're gonna get pitfalls when you are talking about images that it has not seen. So, for example, part of the novel view synthesis is that you had this camera, and you had this camera that they took this picture, and they took this picture. And these pictures usually have some overlap of the scene, but now you want to create this camera here that is further. It has probably some more stuff in there. And the question is now, what happens if I am moving my camera in these areas that don't exist? And this is where usually the reconstruction breaks, because in these areas you get popping, ghosting, some of the blurring effects. And if I am just comparing like this result here with the ground truth that I have, LPIPS is not really gonna catch these effects that happening in between. And it's gonna say that, oh, it's quite similar, it looks okay. But to a human eye, it just looks off right away. So that's where LPIPs fall short. Now that we talked about all these measurements, let's say that you get a model and you have your paper, and at the end of the paper you're gonna see a table that it lists all three of these and is reporting a number for all of these. How do you read the paper and how do you evaluate it? First of all, you need all three of these. So if you have a measurement that is scoring like really good on these two and really bad on LPIPs, you're probably, if you go to the images that they provide for their reconstruction results, you are able to see what's wrong. So if LPIPS is off, if LPIPS is low, usually it is very obvious to human eye. But let's say you got another model. Let's say you want to compare 3D GS with another model. So this is a new model. And 3D GS is scoring really high on SSIM. One thing you need to do is that when you're comparing models in the paper, you need to go to the loss function and see how they're computing loss. Because in 3D GS, they use L1 plus 1 minus SSIM. So technically, 3D GS is training on the metric that they are reporting on. It's a little bit cheating, but not really, because like you need some way to communicate loss to the models, and these are one of the good ways of like describing where things are off. So if you're having a new model that is scoring really high on LPIPS, really high on a PSNR, not doing as well on SSIM compared to 3DGS, you don't think of it as like, oh, this is a bad model. You know the result is because like, oh, this model probably didn't like check the loss and see if the loss is not trained on SSIM. And if it's not trained on SSIM, then it's very likely that's not going to perform as well as 3DGS. So it's important to check the loss and decide what is what. One more thing about papers, and this part is about replicating results. So if you're replicating results, one thing that is very important, especially about LPIPS, is that you want to use the same backbone that the other study used as their backbone. So there are two backbones for LPIPS that they are very common. It's VGG, and the other one is Dino. And so if you get the wrong backbone and compare, your results are going to be off. So what you want to do is that if you're replicating a paper, go get their data set, and on the same data set and the same seed, do one of the reconstructions and then compare metrics. And you need to be in the margin of error too. So like you want to be at 0.05 margin around this number. And if you're not, probably you're using the wrong backbone or something else is wrong. So that's it for today. Now you know when you are looking at papers what to care for. Thank you.